In this lecture, I will discuss the concepts of center of mass and linear momentum and the associated principles and theorems that are used to describe the application of those concepts in various physical systems. First, let's begin with the concept of center of mass. So far, we have discussed objects which we've considered to be point particles. So that means these objects did not have actual physical dimensions which were considered in solving problems. So we ignored the physical dimensions. We only were concerned with the mass of those objects. And we said that objects with finite physical dimensions would behave the same way as if all of the mass was focused at a point in space, and thus we looked at those objects as point particles. So we are going to now establish a relationship between the knowledge of a point particle and also the dimensions of the object in a way that explains better why we would focus the mass of the object at that particular point and thus consider it a point particle when applying Newton's laws and the equations of kinematics. As an example, let's look at the motion of a baseball bat that is tossed in the air. As you can see from the drawing, and you've probably seen examples of objects that do not have a round shape tossed in the air, the baseball bat will, in general, undergo two separate types of motions combined into one. So the baseball bat is going to rotate about a specific point somewhere inside the volume of the bat. So as the bat is traveling through the air, it is rotating. But at the same time, this specific point inside the baseball bat is undergoing a motion along a parabola. So this is a complex motion that involves rotation. And as I said, there is a special point in this object for which the motion is simple. This special point inside the baseball bat is the center of mass. And the center of mass of the bat traces out a parabola. So the center of mass of the baseball bat behaves, as it moves through space, behaves as a simple projectile. And all other points of the baseball bat rotate about the center of mass as it's moving through space. In this context, I can state the following definition for the center of mass, or COM, of a system of particles. The center of mass of a system of particles is the point that moves as though, first, all the system's mass were concentrated there, and second, all external forces were applied there. And this is the connection between the previous considerations of all finite-sized objects being point particles and the center of mass. So again, the center of mass is a point in space of a system of particles or objects that moves as though all of the system's mass were concentrated there and all external forces were applied there. Now let's discuss how to find the position of the center of mass of a system of particles in space. Let's consider a system of particles with masses m1, m2, m3, and so on and so forth until we get to the nth particle with mass mn. I'm going to discuss a one-dimensional case here because it's the easiest to sketch, and a three-dimensional case will be just a generalization of the one-dimensional case. I'm also going to introduce a one-dimensional coordinate axis with origin at point O and positive orientation to the right. And in this one-dimensional coordinate system, I'm going to measure the positions of each particle with respect to the origin. So the first particle has position x1, the second particle has position x2, the third particle will have position x3, and so on and so forth. The nth particle will have position xn. Then I can construct the following ratio. The ratio will be the sum of the products of the mass of each particle and the distance from the origin, divided by the total mass of the system of particles. So we have m1 times x1 plus m2 times x2 plus m3 times x3 plus, and so on and so forth until we get to the last particle, that is mn divided by xn, multiplied by xn. And then I'm going to divide this denominator by the total mass of the system of particles, which is m1 plus m2 plus m3 plus, and so on and so forth, plus mn. And I'm going to call this the coordinate of the center of mass of this system of particles along the x-axis. So this is x, this is the position of the center of mass of this system of particles in space, and this is a one-dimensional space. Therefore, the center of mass will be somewhere along the x-axis. So as you can see from this definition, the position of the center of mass is determined by, obviously, the masses of the particles, but also by the positions of these particles in space, which means that if the positions here are changed, then the terms in the sum will have different values compared to this particular configuration, which then will change the position of the center of mass of this system. So the position of center of mass of the system is highly dependent on the position of the individual members of the system with respect to the selected origin of the coordinate system. So then I can rewrite the expression for the x-coordinate of for the coordinate of the center of mass for the system that I discussed, replacing the total mass or the sum of individual masses with capital M for the total mass as 1 over m times the sum of mi times xi, where I starts from 1 and ends at n. And n is the number of particles in that system. Then I can use this expression to generalize for three-dimensional mass distribution. We already have an expression for the x-coordinate of the center of mass. For the y-coordinate of the center of mass, the sum simply changes to mi times yi, where yi is the y-coordinate of each particle in a three-dimensional space. And then we have the z-coordinate of the center of mass, which is defined by the sum of terms mi times zi, where zi is the z-coordinate of each mass in a three-dimensional space. So in a three-dimensional space, the center of mass position is a vector, and this is these are the components of that vector. So the x component, the y component, and the z component. Now let's look at an example that will show us how the positioning of the particles in a system changes the position of the center of mass. Let's look at two different configurations here. We have two masses, m1 and m2, placed in a two-dimensional coordinate system, while both masses are located along the x-axis. Mass m1 is located at the origin of the coordinate system. Mass m2 is located a distance d from the origin. So then the center of mass has a coordinate x, that we can calculate by using the definition, and the expression for the center of mass coordinate will look like so. This is the expression. So notice that in the general formula for the calculation of the center of mass, we have the first term is the mass of the first particle times the position of the first particle, or the coordinate of the first particle with respect to the origin, plus the mass of the second particle times the distance of the second particle from the origin. In our particular example, the particle m1 was located at the origin, therefore the distance from the origin was 0. And thus, the first term in the numerator is 0. Now let's look at a different distribution of the particles in the system. Mass m1 is a distance x1 from the origin, and mass m2 is a distance d from the first particle, or a total of distance x2 from the origin. So now the position of the center of mass is calculated with the following expression. The product of the mass of the first particle and the distance from the origin plus the mass of the second particle times the distance of that second particle from the origin divided by the total mass. Now let's substitute some numbers in those two expressions and let's see what the results are. Let's take the two masses to be related as mass m1 times 2 is equal to m2, and let's for simplicity call the two masses. Let's replace m2 with m. So therefore m2 becomes m, and 2 times m1 becomes 2 times m. This is going to make it a little bit easier to cancel out the masses when we plug these in the expressions for the position of the center of mass. So for the first mass configuration, the expression for the coordinate of the center of mass was m2 times d divided by m1 plus m2. Let's substitute. And this gives us md divided by 3 times m. So this is d divided by 3. Let's do the other mass configuration here. Substituting the masses, we get m times x1 plus 2m times x1 plus 2m times d divided by 3m. Now let's make one more simplification. I'm going to set the distance x1 right here to be equal to d divided by 2, so to have this distance d here. So x1 is equal to d divided by 2. So then if I plug in that in the expression here, and after I simplify everything, this gives me 7/6 d. So as you can see, just changing the position of the system of particles with respect to the origin of the selected coordinate system changes completely the position of the center of mass with respect to the origin of the coordinate system. As I discussed already, for a system of particles in space, the x, y, and z coordinates of the two-dimensional position vector for the center of mass are given by those three expressions. So then I can combine the three to write down the actual position vector of the center of mass in 3 dimensions. And so r com is equal to 1 over m, where m is the total mass of the particles in the system, times the sum of mass times position vector for each individual particle. So this term here is the product of the mass of each particle in the system times the position vector for each particle of the system. Note that this position vector here is a 3-dimensional vector, and it consists of the x, y, and z coordinates of that particle in space. So as a reminder, Ri as a vector is xi, I hat, plus yi, j hat, plus zi, k hat. This result here can be generalized for a solid body that consists of infinite number of particles. To be able to calculate the position of the center of mass, we must replace the sums with integration. So that happens by taking the limit when the number of particles approaches when n approaches infinity. In this case, these sums will transform into integrals, and so the coordinate of each of the coordinates of the center of mass in 3-dimensional space will be calculated by those 3 integrals. And here, m is the mass of the object. In calculating those integrals, we are going to limit ourselves to dealing with objects that have a reasonable amount of symmetry and also constant density. That then leads us to the opportunity to change the integrals to be integrals over volume rather than integrals over mass. And since we're dealing with symmetric shapes, that makes calculating those integrals easier. We know that for an object made from certain material or substance that is uniform in composition, the density will be a constant. So the density doesn't change, which means that if I separate or divide the object into small mass elements with mass dm and volume dv, if I take the ratio dm dv, that will be the density of the material from which this object is made. But that also density will be calculated by dividing the total mass of the object by the total volume of the object. Remember, density is constant, and so if I divide a certain amount of mass by its volume, I'm going to get the density of that object. Then I can use that relationship right here to express the mass element dm in terms of the volume element that corresponds to it, dv. And then the integrals that I discussed here can be rewritten in terms of volume elements. And so the coordinates of the center of mass of a 3-dimensional object with constant density are calculated with those 3 integrals. What is also good about that way of representing the coordinates of the center of mass is that if there is symmetry for the object at hand, then one or more of those integrals can be bypassed. Meaning you will get the same result for one or more of those coordinates of the center of mass by simply changing the variable due to symmetry. Some considerations about the symmetry of an object and the position of the center of mass. First, the center of mass lies at a point of symmetry if there is one. So, for example, for a straight line, a point of symmetry will be the middle of the line. So that will be the position of the center of mass. The center of mass also lies on a line or a plane of symmetry. For example, for a rectangle, the center of mass will lie at the intersection of the two diagonals. So this is a line of symmetry. For a rectangular prism like this one, the center of mass is going to be located at the intersection of the diagonals. So this is where the center of mass is. For some objects, the center of mass need not be on the object. And the simplest example is a donut. So a donut is a shape that approximately looks like so, and the center of mass is located at the geometric center where there is no material from the donut. Another example of the center of mass being positioned outside of a shape would be something that looks like that. The center of mass will be somewhere outside of the shape itself. Before we discuss Newton's second laws applied to an object considered to be a point particle. Now let's apply Newton's laws to a system of particles considering the center of mass of that system. First, let's point out that the center of mass motion continues unaffected by forces internal to a system. For example, a system of billiard balls which collide with each other is an example of the center of mass of that system moving unaffected by the internal forces of the system. So what that means is that for a system of particles, no matter how many there are, if the forces that are present only come from interactions between those particles, then the center of mass will move unaffected by those forces. So when we're discussing the motion of the center of mass of a system, Newton's second law will have to be rewritten or changed notation a little bit to reflect that. So the net force will be equal to the product of the mass of the entire system times the acceleration of the center of mass. So again, we are no longer talking about the entire system of particles being considered a point particle. We are now talking about the entire system moving the way its center of mass is moving. So since this is a three-dimensional vector equation, it can be written in terms of components along each coordinate direction as the net force in x direction is equal to the total mass of the system times the acceleration of the center of mass in x direction. Then we have the y component of the net force is equal to the product of the mass of the system and the acceleration of center of mass in y direction, or the y component of the acceleration of the center of mass. And then finally we have the z component of the net force is the product of the mass of the system and the z component of the acceleration of the center of mass. Just as a reminder, F net is the sum of all external forces. So again, external forces, very important. The internal forces do not count. M is the total mass of the system. And it's important to also remember that this is a closed system, meaning that particles do not leave the system, particles do not get added to the system. So the number of particles in the system is constant at all times. That is the only way the mass will be constant. And finally, as I already stated, ACOM is the center of mass acceleration. Before we move on, let's talk about how we can calculate the velocity of the center of mass and also the acceleration of the center of mass. We know from before that the velocity of moving objects is the time derivative with respect to the position function of the object. So then I can apply the same definition for the position of the center of mass. So this leads to Vcom equal to drcom dt, which is the dt of rx I hat plus ry j hat plus rz k hat, and of course these are the coordinates of the center of mass. And so then the derivative will be distributed across all the terms in the sum, and then this becomes d dt of rx com I hat plus d dt of ry com j hat plus d dt of rz com k hat. Or in other words, this is v com x I hat plus v com y j hat plus v com z k hat. And so to summarize, the components of the velocity v com x is the r com x dt, v com y is the r com y dt, and v com z is the r com z dt. Let's highlight those three. And now let's do the acceleration of the center of mass. So again, we start with the general definition of acceleration, and that is the acceleration is equal to dv dt. So therefore, for the acceleration of the center of mass, ACOM, it's going to be calculated as the time derivative of Vcom. So this will be the sum d dt of Vcom x I hat plus d dt Vcom y j hat plus d dt Vcom z k hat. Or this is ACOM x I hat plus ACOM y j hat plus ACOM z k hat. Or in other words, the components of the acceleration of center of mass are ACOM x is d dt of Vcom x, ACOM y is d dt of Vcom y, and ACOM z is d dt of Vcom z. Let's now define a new physical quantity associated with the motion of objects. That new quantity is called linear momentum. Linear momentum is a vector quantity p, which is equal to the product of the mass of an object and the velocity of the object. From the definition here, you can see that the linear momentum is a vector that has the same direction as the velocity of the object. The units for momentum will be the units of mass, kilograms, times the units of velocity, which is meters per second. Pay attention to the unit here. The unit here tell you that when you're calculating the momentum of a moving object, you always must convert the mass in kilograms, and you always must convert this velocity into meters per second. Since the linear momentum is associated with the velocity of the moving object, that means that the linear momentum can only be changed by a net external force. The time rate of change of the momentum of a particle is equal to the net force acting on the particle and it's in the direction of that force. So what that statement says is that if I take the time derivative of the momentum dt dp, that will be, of course, equal to ddt of m times v. And since the mass is a constant, I can then rewrite this as m dv dt. But we know that dv dt is simply the acceleration, and so then this becomes m times a, which is nothing but the net force acting on the object. And so we can write Newton's second law, F equals to ma, in terms of the time rate of change of the momentum, or in other words, the net force acting on an object, is equal to dp dt. So this expression here is written for an object that is considered to be a point particle, or for point particle in general. Now I can also rewrite this expression for a system of particles, considering the motion of the center of mass under the action of that net force. First, for a system of particles, the linear momentum P will be equal to the product of the mass of the entire system times the velocity of the center of mass, v com. Then, taking the time derivative, we can write Newton's second law for a system of particles as the net force acting on that system of particles is equal to the time derivative of the linear momentum of the entire system. So from this expression, it follows that the net external force on a system changes the linear momentum of the system, and also that without a net external force, the total linear momentum of a system of particles cannot change. A question can be asked, such as, to change the linear momentum of a particle or a system of particles, an external force must be applied, and we know that. But where does this external force come from? It can simply come from interaction with a single particle or a system of particles. And this interaction between two particles or between two systems of particles is known as collision. So, a particle experiences external net force, or a system of particles experiences external net force when it undergoes collision with another particle or system of particles. In a collision, momentum of a particle can change. So during the collision, we can define a new physical quantity, which is called impulse, J, as a vector quantity that is calculated by this integral. So this is an integral between two moments of time of a force that varies with time, dt. So let's visualize the process. Consider a baseball that is being hit by a baseball bat. So we know that the baseball is a perfectly round object. And so when it's getting hit by the baseball bat, the interaction between the two objects is not instantaneous. As a matter of fact, it takes some certain amount of time for the baseball to be stopped moving by the interaction with the baseball bat, and then to go in the opposite direction. So That means that the baseball experiences a certain amount of force from the baseball bat, and this interaction, the time for which the force was applied on the baseball, is not infinitely small. It actually has a certain measurable length. During that period, the baseball, as you can see, will deform until it completely stops moving towards the baseball bat, and then it's going to bounce back and move in the opposite direction. So that also means that the force that the baseball bat applies on the baseball is not a constant force, but it changes with time. And so this integral here for the impulse generated during the collision between the baseball and the baseball bat in this example includes this force which changes with time, and the integrals is over time, because the interaction happens for a finite amount of time. Now, what happens to the momentum of the baseball as it hits the baseball bat? The momentum of the baseball changes. How? Well, the baseball initially is moving towards the baseball bat, and the baseball has a certain velocity and certain mass. Therefore, the baseball has a certain momentum. But once it interacts with the baseball bat, it changes direction of motion. So therefore, the velocity will be different, and the momentum of the baseball will be different. So there is a change in momentum before and after collision with baseball bat, and this change in momentum must be related to the force applied by the baseball bat on the baseball and the time of interaction between the two objects. Or in other words, there must be a relationship between the change in momentum and the impulse generated during the collision. And this relationship is very simple. The applied impulse is equal to the change in momentum of the object during the collision. Or in other words, the change in momentum is equal to J, the impulse generated during collision. And this is known as the linear momentum impulse theorem, or simply impulse momentum theorem. This equation can be written component by component like other vector equations. Remember that in general, these vectors here are three-dimensional vectors. So we can simply write for each coordinate direction that delta px is equal to jx, delta py is equal to jy, and delta pz is equal to jz. Now, calculating this integral is not necessarily doable in some situations. However, instead of using this force that changes with time, we can average the force over time, which then is going to simplify the calculation of the integral. So, the plot of force versus time for a force that changes with time can look like this curve here. And calculating the integral from the previous slide simply means finding the area under the curve. However, if I average this force between the two timestamps here, t initial and t final, that is going to then result in a shape of the force versus time that is very simple, and the area can be calculated without integration. And so, in this course, we are mainly going to deal with average constant force. And then in this case, the impulse generated by the force is simply the average force times the time interval over which this force was applied to an object. Now we are ready to talk about conservation of linear momentum. Let's consider a closed, isolated system, which means that the system does not interact with its surroundings, which also means that there can be no net external force acting on the system. Or in other words, the net external force acting on the system is 0. Means that the impulse that will be acting on the system is equal to 0, which means that the change in momentum will be equal to 0. Well, when the change of momentum is equal to 0, that simply means that the momentum of the system is constant at all times. So, when the impulse on the system is equal to 0, we say that if no net external force acts on a system of particles, the total linear momentum P of the system cannot change. And this is known as the law of conservation of linear momentum. In three-dimensional cases, you can also check the components of the net external force that is applied to a system. And so, if the component of the net external force on a closed system is 0 along an axis, then the component of the linear momentum of the system along that axis cannot change. So even though the net external force may not be 0, if a certain component of the net external force is 0, that means that the linear momentum of the system along that coordinate direction cannot change, or it doesn't change. Objects can undergo different types of collisions. First, we have elastic collisions. Elastic collisions are collisions for which the total kinetic energy of the system is unchanged before and after collision, which means that for all the particles that are in the system, the sum of all kinetic energies before collision is equal to the sum of all kinetic energies after collision. Of course, this is an ideal approximation, and for our purposes, when we consider elastic collisions, we are always assuming that the conditions are ideal for those collisions. In reality, of course, energy is always transferred between the objects during collisions, so in reality, the total kinetic energy will never be conserved. But again, for our purposes, when we consider elastic collisions in various problems, we are always going to assume that the total kinetic energy is conserved before and after collision. Another important feature of elastic collisions is the fact that the collisions between the objects happen, the objects do not change shape. So you can think of an elastic collision example being the collision between two billiard balls. Visibly, we cannot detect change in shape when two billiard balls collide with each other. Microscopically, there is of course small deformations, but if we just constrain ourselves to simply looking at the two billiard balls colliding, we can't see those deformations, so for our eyes, this is a perfect elastic collision. And so the kinetic energy of the system before and after collision should be the same. The second type of collisions is the inelastic collisions. So during inelastic collisions, some energy is transferred from the system, so energy leaves the system, which means that the kinetic energy before and after the collision is not conserved. So let's summarize that. The kinetic energy initial is not equal to kinetic energy final. As a matter of fact, kinetic energy initial should always be bigger than kinetic energy final. And for elastic collisions, kinetic energy initial is equal to kinetic energy final. Examples of inelastic collisions are, for example, a basketball dribbled on a floor. When the basketball collides with the floor, the ball changes shape slightly. When it bounces off the floor, it restores shape. But some of the energy, the kinetic energy that the ball had before collision, is used to restore the shape of the ball back to completely perfect round shape. And then some of the energy was transferred from the system in the form of sound energy. And depending on the particular inelastic collision, you also may have friction generated, which then will transfer energy from the system in the form of thermal energy. And then finally, a division of inelastic collisions are the completely inelastic collisions. So completely inelastic collisions are collisions for which the objects get stuck together. For example, imagine you have two spheres made of clay that are collided with each other, and then they get stuck together and move as one object with the combined mass of the two spheres. Or you can think of train cars on a railroad and another train car coming towards them, colliding with them, and then they're all stuck together, moving as one object. So these are examples of completely inelastic collisions. Those types of collisions have the greatest loss of kinetic energy, and of course in general the kinetic energy before collision and after collision they are different, and the initial kinetic energy is always larger than the final kinetic energy. So if you ever were asked the question whether a collision was elastic or inelastic, all you need to do is compare the kinetic energies before and after collision and see if they are equal or if they are not equal to each other. One important detail to keep in mind when you are dealing with collisions of objects is that the linear momentum is always conserved. So it doesn't matter whether the collision is elastic or inelastic or completely inelastic, the linear momentum is always conserved. Now let's look at a one-dimensional inelastic collision. So one-dimensional inelastic collision of two objects. Here are my two objects, a mass m1, a mass m2, and those two masses are moving in positive x direction with velocities v1 initial and v2 initial. And so after they collide, mass m1 is moving with velocity v1 final, mass m2 with velocity v2 final. Both again are moving in positive x direction. So conservation of linear momentum states that the linear momentum of the first particle plus the linear momentum of the second particle, m1 v1 initial plus m2 v2 initial, must be equal to the linear momentum of the first particle plus the linear momentum of the second particle after collision. So this is m1 v1 final plus m2 v2 final. This relationship here can be, of course, used for particle 2 moving in negative x direction or towards particle 1, like so. So when that is the case, if you know the values of those two velocities, all you need to do is replace them here and here with minus signs, since the direction of motion is opposite to positive direction. So in general, when you are writing the conservation of momentum equation and you are substituting velocities, you must of course account for direction of motion with respect to the positive direction of the coordinate axis. And so the values will enter here with pluses or minuses depending on the direction of the velocity. If you do not pay attention to the signs, then your answers will be wrong. For a completely inelastic collision, such as mass 1 is moving towards mass 2 with some initial velocity, and mass 2 being at rest, the conservation of linear momentum still applies. This expression here will be modified to account for the particular physical situation in the example. Since the second mass is not moving, this term here will be equal to 0. So what we are left with is mass 1 times v1 initial. And then after collision, the two objects are stuck together and move as one. Remember, this is completely an elastic collision. So that means that this new object has a combined mass of the two objects and now is moving with some velocity v. So then this right side of the conservation of linear momentum expression, you simply change to the sum of the two masses times the velocity with which that new object is moving. Then from here, I can calculate the velocity with which the system moves after collision, and that would be m1 v1 initial divided by m1 plus m2. In a closed isolated system, the velocity vcom of the entire of the center of mass of the system cannot be changed by a collision because with the system isolated, there is no net external force to change it. So to get an expression for vcom, let's again look at the previous example where we have a stationary mass and a different mass that is moving towards it with some initial velocity. So in this configuration, the velocity of the center of mass will be a constant before collision because the velocity of the moving particle doesn't change before collision. And so then for the system of particles, we can say that the total momentum P is equal to the total mass of the system m times v com, or in other words, this is m1 plus m2 times v com. Well, then I can rewrite or rearrange the terms here to get an expression for vcom, and that simply becomes vcom is equal to p divided by m1 plus m2. But remember that P is the total momentum of the system of particles. Or in other words, P is equal to P1 initial plus P2 initial. So then I can also write that vcom is equal to P1 initial plus P2 initial divided by m1 plus m2. Or in other words, the center of mass velocity remains unchanged in an absence of an external net force for a system of particles, even if the particles undergo collisions. And here we have a plot of the velocity of the center of mass as the system of particles initially is in a configuration where there is no collision, and the first particle approaches the second particle, they collide right here, and then they continue to move as one object. And so as you can see, the velocity of the center of mass remains unchanged, it remains constant. Again, this is because there is no external net force applied to the system. The forces in the system here are only internal. Let's now look at elastic collisions in one dimension. I already stated that the total kinetic energy is conserved in elastic collisions. In an elastic collision, the kinetic energy of each colliding body may change, but the total kinetic energy of the system doesn't change. So we can have two different situations here. We have one object is moving and the other one is stationary target. So the second object here is stationary, the first object is moving towards it with some initial velocity. And then after collision, both objects are moving with different velocities. In this case, applying the conservation of linear momentum tells us that the linear momentum of the system before collisions, which only equals to the linear momentum of the first object, is equal to the sum of the linear momenta of the two objects after collision, here and here. And also that the kinetic energy of the system before collision, which is simply the kinetic energy of the first object, is equal to the kinetic energy of the system after collision, which is the sum of kinetic energies of the first and second object after collision. So from those two equations, I can solve for the velocities of the two objects after collision, v1 final and v2 final. You can use these expressions on your formula sheet without having to derive them for the next test. This is as a side note. From those expressions for the final velocities, I can get specific expressions depending on the relationships between the masses of the two colliding objects. If the two masses are equal, so m1 is equal to m2, then the final velocity of the first object will be equal to 0 because the difference here is 0. So the final velocity of the first object is 0. And the final velocity of the second object will be equal to the initial velocity of the first object. Or in other words, if you think about two billiard balls colliding, and one of them stationary, after collision the ball that was moving will be stationary and the ball that was stationary will be moving. This should be happening in an ideal collision. Of course, in reality, since there is some friction involved in the process, both balls will be moving. But if you could completely remove friction from the collision and the generation of sound energy, you would observe that the stationary billiard ball will be moving after collision and the billiard ball that was moving before collision will become stationary. For a massive target, which means object 2 is much heavier than object 1, the final velocity of the first object will be approximately the opposite of the initial velocity of the first object, which means that the object just bounced back from the target. So you can think of this situation, for an example, a collision between a golf ball and a cannonball. So the golf ball hits the cannonball and it bounces right back in the same direction from which it came from, and the velocity with which it's going to go back will be approximately the same as the velocity with which it was initially moving. And then the cannonball, or the target, will be moving with velocity v2 final, which is proportional to the initial velocity of the moving object before collision, this one. And the coefficient of proportionality will be given by this ratio here. So depending on what's the ratio specifically between the two masses, that will determine what will be the final velocity of the target after collision. The last possible situation is when the target is very light and the projectile is very massive. So M1 is very large and M2 is very small. So you can think of this being a cannonball and this being a golf ball. So what's going to happen is we can ignore the mass of the target, M2, and so the initial, the final velocity of the projectile will be equal to the initial velocity of the projectile approximately. And then the final velocity of the target, the golf ball, will be approximately 2 times the initial velocity of the projectile, the cannonball. So again, when the target is much lighter than the projectile, we ignore the mass of the target. For a moving target and moving projectile, the conservation of linear momentum and kinetic energy expressions change a little bit. We have 2 terms for before collision for the linear momentum and 2 terms after collision, and the same for the kinetic energy. And so this is a system of 2 equations for which we can use to find the final velocities of the projectile and the target after collision. After doing some algebra, the expressions are listed here. As you can see, these are not simple expressions, and the derivation is just tedious algebra, so I'm not going to show it here. You can do it to practice a little bit manipulation when working with those systems of equations. However, consider you know the initial velocities of the 2 objects, the target and the projectile. When you are substituting here in these formulas to find the final velocities, you must be careful about the direction of motion with respect to positive orientation of the coordinate axes. So in this particular example, when the two objects are moving in opposite directions, V1i will be entering the calculations with a positive value because it's directed in positive x direction. But V2i will be entering those calculations here with a negative value because it's directed in negative x direction. So this is a very important consideration that you must pay attention to, otherwise your results will be wrong. The formalism of linear momentum in conservation of energy can be extended to two-dimensional collisions. So conceptually, two-dimensional collisions are no different than one-dimensional collisions. However, mathematically, the procedure of finding final velocities is a little bit more complicated because of the presence of angles with respect to the coordinate axis now. Remember that conservation of linear momentum is a vector equation. That means that one can write the conservation of linear momentum for each coordinate axis. And the same applies for the kinetic energy equation. So the kinetic energy equation can be divided in two equations, one for each coordinate axis. And so then the previous formalism for one-dimensional collisions can be applied in those two-dimensional situations for each coordinate axis independently, and then the results can be combined to find the final answer for the final velocities. So here is a simple example that illustrates the principle. We have a stationary target with mass m2, and we have a projectile with mass m1 with initial velocity v1 initial moving along the x-axis. After collision, the two particles move along those two directions. And so the final velocities make those angles with the x-axis. So I can write the conservation of momentum along the x and y axis as shown here in those two equations. And as you can see now, there is trigonometry involved in the expressions. And then I can write the conservation of kinetic energy as shown here. And so now I have a system of three equations for three unknowns. A system of three equations for two unknowns, V1f and V2f. So solving this system will give me solutions for the final velocities of the two particles after collision, and also information about these angles if I need it. So the formalism again is pretty similar to one-dimensional situations, provided that you are able to separate the linear momentum equation into equations along the x and y direction. Let's now do some example problems to illustrate the application of the concepts in this lecture. You throw a ball with a mass of 0.4 kilograms against a brick wall. It hits the wall moving horizontally to the left at 30 meters per second and rebounds horizontally to the right at 20 meters per second. First, find the impulse of the net force on the ball during its collision with the wall. And second, if the ball is in contact with the wall for 0.01 seconds, find the average horizontal force that the wall exerts on the ball during the impact. So here is a sketch of the problem. The ball is initially moving towards the wall, hits the wall, bounces back off. The speed of the ball before collision is 30 meters per second, and after collision is 20 meters per second. So since the ball initially is moving in negative x direction, the speed will be calculated, or will enter calculations with minus sign in front of it, and then after collision, the final speed of the ball will enter calculations with a positive sign. Let's write down the momentum of the ball before and after collisions. Before collision, the initial momentum of the ball is 0.4 kilograms times negative 30 meters per second, so this is minus 12 kilograms meters per second. And the after collision momentum of the ball is 0.4 kilograms times 20 meters per second, or this is 8 kilograms meters per second. Since we want to find the impulse of the net force on the ball during collision, we then must calculate the change in momentum, because by definition the change in momentum is equal to the impulse. So delta px will be equal to jx. Or in other words, we have px final minus px initial is equal to jx. Px final is 8 kilograms meters per second. Px initial is minus 12 kilograms meters per second. And so the result of this calculation is 20 kilograms meters per second. In terms of the units for impulse, remember the impulse is force applied for some time. This has units of Newton seconds. So the change in momentum is 20 kilograms meters per second, or in other words, that is 20 Newton seconds. So this is the impulse that acts on this ball. Next, we want to find the average horizontal force that the ball exerts on the ball during the time of impact, and the time of collision or of impact is 0.01 seconds. So for that, I'm going to use the relationship between the impulse and the average force and time of interaction. So the average force in x direction will be equal to jx divided by delta t. That is 20 Newton seconds divided by 0.01 second. And this is going to give us 2000 newtons. Now let's do the following example. So two gliders with different masses move toward each other on a frictionless air track. After they collide, glider B has final velocity of 2 meters per second. What is the final velocity of glider A? How do the changes in momentum and velocity compare? So here are the two gliders. The initial velocity of glider A is 2 meters per second to the right in positive x direction. The initial velocity of glider B is negative 2 meters per second, that is in negative x direction. They collide. After collision, glider B is moving with 2 meters per second in positive x direction. What's the velocity of glider A after collision? The masses of the two gliders are 0.5 kilograms for glider A and 0.3 kilograms for glider B. The conservation of linear momentum states that the linear momentum of the system before collision must be equal to the linear momentum of the system after collision. The linear momentum of the first glider before collision is ma, va, initial x, and the linear momentum of glider B before collision is mb times vb, initial x. After collision, the linear momentum of glider A is ma times va fx, and the final momentum of glider B is mb times vb fx. So the initial momentum, so this is equal to 0.5 kilograms times 2 meters per second plus 0.3 kilograms times negative 2 meters per second. Remember that glider B is moving in negative x direction before collision, so that's why the minus sign here. And then after collision, we have 0.5 kilograms times VA Fx. We are looking for that velocity, plus 0.3 kilograms times 2 meters per second. So then I can solve for VA Fx. Rearranging the terms in the expression here gives me that the final velocity of glider A is negative 0.4 meters per second, which means that glider A after collision was moving in negative x direction. The second part of the question here is how do the changes in momentum and velocity compare? For glider A, the change in momentum, PA final minus PA initial, will be the mass A times VA final x minus mass A times VA initial x, which gives us negative 1.2 kilograms meters per second. And for glider B, the change in momentum, PB final minus PB initial, is equal to MB VB final x minus MB VB final, that should be initial, so initial x. Substituting the numbers gives me plus 1.2 kilograms meters per second. Now also we need to calculate the changes in x velocities. Let's see how they compare. For glider A, the change in velocity is negative 2.4 meters per second, and for glider B, the change in velocity is positive 4 meters per second. Let's do one more example. This is a classical example of the application of conservation of linear momentum and also conservation of energy. In the figure, a ballistic pendulum, which is a simple system for measuring the speed of a bullet, is shown. A bullet of mass mb makes a completely inelastic collision with a block of wood of mass mw, which is suspended like a pendulum. After the impact, the block swings up to a maximum height y. In terms of y, mb, and mw, what is the initial speed v1 of the bullet? So this is the ballistic pendulum. This is the block of wood with mass mw suspended with two strings, and it can swing left and right like a simple pendulum. Here is the bullet with mass mb. The bullet hits the block and it gets stuck in it, and then the system block plus bullet starts to swing up as a pendulum. And so the question is, in terms of the height to which the pendulum is going to swing, the mass of the bullet, the mass of the wood, what's the initial speed of the bullet? And let after collision the bullet block system move to the right with velocity v2. Then from conservation of the linear momentum, we get that the linear momentum of the system before collision, which is just the linear momentum of the bullet, is going to be equal to the linear momentum after collision, which is the combined mass of the bullet and the wooden block times the velocity v2 with which the bullet block and block move together to the right. So from here, the velocity of the bullet will be simply equal to the mass of the bullet plus the mass of the wooden block times v2 divided by the mass of the bullet. Now there is a problem here, and that is we do not know v2. So we need to find that. Well, to find v2, we are going to use conservation of energy. For all intents and purposes, the block bullet system simply behaves like a pendulum, like what we've discussed in the previous lecture. So the pendulum has mass m bullet plus m wooden block, initial velocity v2. It swings up and gets to a height y, where it stops. So v final here is equal to 0. So I can use the fact that the mechanical energy is conserved in this example to figure out what is the initial velocity here. Conservation of energy gives me that 1/2 the combined mass bullet and block times v2 squared is equal to the mass of bullet plus the mass of the block times g times y. And so the masses cancel out. And from here, v2 is equal to square root of 2 times gy. So now I can substitute this into the expression for v1. And V1 is equal to mb plus mw times square root of 2 times gy divided by mb. Now let's give some values to these numbers and see what the results will look like. Let the mass of the bullet is 5 grams, the mass of the wooden block 2 kilograms, and the height to which the pendulum swings 3 centimeters. Don't forget to convert the mass here in kilograms and the distance here in meters. And so substituting these values for V2, we get square root of 2 times 9.8 meters per second squared times 0.03 meters. That gives us 0.767 meters per second. And then for V1, we get 0.005 kilograms plus 2 kilograms times 0.767 meters per second divided by 0.005 kilograms. That's going to give us 307 meters per second. Let's calculate the initial kinetic energy, which is just the kinetic energy of the bullet. So this is 1/2 times 0.005 kilograms times 307 meters per second squared. So that gives us 236 joules. And then the final kinetic energy is 1/2 mass of bullet plus mass of wooden block times V2 squared. So this is 1/2 times 0.005 kilograms plus 2 kilograms times 0.767 meters per second, which gives us 0.59 joules. As you can see, first of all, this is a completely inelastic collision. Completely inelastic collision was a collision for which the two objects after collision get stuck together and move as one. And so that's what happens when the bullet hits the block. It gets stuck in the block, it gets lodged in the block, and then the system block bullet moves together as one. So in completely inelastic collisions, there is a loss of kinetic energy during collisions. And so as you can see, this loss is pretty significant here. Before collision, after collision. The loss here is through the force of friction generated between the bullet and the block. And the loss here is in the form of heat that was generated during the collision. With this, I'm going to conclude the lecture on linear momentum.